All right, so now now we know how what an implicit equation is, we're gonna look at how do we do derivatives of implicit equations. All right, so we're still gonna use the same tools that we had before to take derivatives. There's only one difference. Because the x's and y's are mixed together, we have to remember that every single time we take the derivative of a y, it's representing this kind of entire output. And that'll kind of give us this mini chain rule we have to do every single time we take the derivative of a y. And then once we have our answer, we're trying to figure out what the derivative is. And we might have to move some things around at the end to figure out what our actual final answer is. All right, so a lot of times when you're doing implicit derivatives, they ask for you dy, dx. But remember, this is the same thing as kind of the f prime we were using before. This is just notation for the derivative of y with respect to x. All right, so we're just doing our normal derivative thing. All right, so as we go through here, we're going to take the derivative of each piece. So we're going to take the derivative of x squared, that's just 2x. Derivative of y squared is 2y. But this is where you have to remember that y is actually an entire function in itself. So this is actually a mini chain rule problem. We do the power rule to get 2y. Then we have to multiply this by the derivative of y, which is dy dx. And that's equal to the derivative of 25, which is 0. All right, so this is really the one thing you have to remember when you're doing implicit derivatives, is that whenever you take the derivative of y, you're going to have to multiply by dy dx at the end. And to get the formula for dy dx, we just have to do a bit of solving. I can subtract 2y from the other side. Or not 2y, 2x. Subtract 2x the other side. And then divide by 2y. Right, and our final answer with some simplifying is negative x over y. All right, so this is what we mean by implicit derivatives. We can take the derivatives of each of these individual pieces, and at the end we solve for the derivative that we care about is negative x over y. So if there was some point like 1, 1 on our graph, we would plug a 1 in here and a 1 in here, and we get the slope of the tangent line at that point. All right, so here's another implicit derivative we have to take. All right, so here we're taking derivative on the left-hand side of x cubed times sine of y. So this is going to be a product rule problem. All right, we're going to keep the first term the same, times the derivative of the second term. And again, remember, these are kind of mini chain rule problems. So the outside we have sine, so take the derivative of that is cosine. Inside of y, the derivative of y is dy dx. Then we add, we keep the first function the same, multiply by the derivative of the second function. On the right-hand side, much simpler, just a power rule. We just get 2. And this one will be similar to the last one. Now we want to solve for dy dx. So we're going to subtract that other term first. I'm just going to write it in a slightly different order because that's probably how you'll see most time with the term in front of the trig function. And then we have to divide to get dy dx all by itself. So I'm dividing by this whole piece down to there so that we get dy dx by itself. So again, now if we knew some x and y value that was on our implicit equation, we would plug it in down here and we'd figure out the slope of the tangent line at that point. Now then we'll start doing some weird things with implicit derivatives as well. This one's asking to find the equation of the normal line of this equation at this point. All right, normal line, well, we have our tangent line. The normal line is just perpendicular to the tangent line. So it's kind of the exact opposite of the tangent line. You're going in the kind of worst direction in terms of the tangent line. All right, so how do we find the normal line? Well, to find the normal line, we first have to find the tangent line. And to find the tangent line, we need to do the derivative. All right, so we're going to do the derivative of this. Derivative of y cubed is 3y squared dy dx. All right, so you do the power rule, and then the derivative of y is dy dx minus derivative of x cubed. And then this, it doesn't really look like it, but it is a mini product rule because we have x times y whenever we're multiplying things. I have a couple different options here. You could keep the negative 3 on the outside and just do the product rule with xy. You think about this as negative 3x and y. All right, what I'm going to do is, think about it as negative 3x as one term and y as the other term. So I'm going to keep negative 3x I'm going to multiply that by the derivative of y, which is dy dx. I'm going to add, I'm going to keep y, and multiply that by the derivative of negative 3x, which is negative 3. And again, solving for dy dx, I'm going to keep the dy dx terms together on this side and move the other terms over. So I'm going to have 3y squared dy dx minus 3x dy dx equals, let's see, I add this to the other side. I'm going to also add this to the other side, plus 3y. And just to save some room on the side, what I would do now is I'm going to factor the dy dx that's common on this side out and divide by the other stuff that's left. So my final answer is going to be dy dx is 3x squared plus 3y all over 3y squared minus 3x. All right, so this is our derivative function. We use this to find the slope of the tangent line. So now I can use my point that I know is on my graph. I can plug 3 halves into here and figure out what the slope of the tangent line is going to be. And so let's do that up here in a different color. And it's just going to be a bunch of simplifying. So 3 halves squared is going to be 9 fourths. So it's going to be 27 over 4 plus 9 over 2 over 27 over 4 minus 9 over 2. I'm getting a common denominator. Adding and subtracting, so 27 plus 18. I feel like I can do that in my head, but at this point, I'm just going to use a calculator. 27 plus 18, 45 over 27 minus 18 is 9. And then dividing by a fraction is the same as multiplying by its reciprocal. So the 4's are going to cancel. I get 45 over 9, which is 5. Right, so a lot of simplifying, but we get that the slope of the tangent line is 5. All right, the slope of the normal line, it's perpendicular, and perpendicular slopes are negative reciprocals. So the slope of the normal line is the negative reciprocal. So instead of positive 5, I'm going to have negative. Instead of 5, I'm going to have 1 over 5. All right, so the slope of the normal line is just perpendicular to the slope of the tangent line. So I get negative 1 over 5. My final answer is going to be, all right, that's the slope. This is the point, so I put it into point slope form. All right, so this is our final answer as the slope of the normal line of that. So you can see all the work that would have to go into this one problem. You have to take the implicit derivative of this. That was down here. Once you have the implicit derivative, you plug in the point you care about to get the slope of the tangent line. Once you have the slope of the tangent line, you find the slope of the normal line, which is just perpendicular, and then you get your final answer there. All right, so a lot of stuff that goes into one problem, but you can kind of see the type of questions and the types of things you might have to do related to implicit derivatives and just other general calc terms. All right, and this one, it seems like we've done this problem before, but now it's asking for this notation. All right, this is just the notation for the second derivative. All right, so earlier we found the first derivative of this implicit equation was negative x over y. And now we just want to do the derivative again. So we take the derivative to the left. We're just going to get the second derivative. On the right, we're going to have to do the quotient rule. So the quotient rule says I keep the bottom times the derivative of the top minus I keep the top times the derivative of the bottom, which is dy over dx, and over the original bottom squared. All right, and then there's a bit of simplifying we can do. Well, the obvious one is we have these negatives that are going to cancel, but also we don't want the first derivative in our equation for the second derivative, but the first derivative we have a formula for. It's negative x over y. So I can say this is negative y, right, plus x times negative x over y squared. Just negative y minus x squared over y squared. And that is our second derivative of this implicit equation. You could probably even do a little bit more simplifying. You could write this as, let's see, multiply top and bottom of y, negative y squared minus x squared over y cubed. All right, so you can do a bit more simplifying and changing things. All right, but again, the second derivative is this notation up here. We just take the derivative again of the answer we got from before, and then remembering that if the first derivative pops up at all, we have an equation for it as well. All right, so just knowing that there's multiple derivatives you can do for any function, but even implicit functions. All right, so in class, we're just going to work on taking these implicit derivatives, and we'll use them to find the derivatives themselves, slopes of tangent lines, equation of normal lines, all the kind of things that we practice in the video. Again, look through the video, see if you have any questions. All right, come to class and ask if you are confused about anything. All right, really, it's just a practice thing. And remember that every single time you take the derivative of y, you're going to get that dy dx, because y is kind of its own function in itself.